Hello, this is Brady Johnson, and I'm going to do the strain rosette problem for ME304 summer. So how I'm going to start this is by writing what the problem gives. And so I'm first going to draw our strain rosette that's shown. And so we're going to have our strain number 2 right here. We'll have our strain 1. Going 75 degrees downward, and our strain 3, he mishandled those lines. Strain 3 going 75 degrees upward. And for that, our strain 1 is going to be negative 150 times 10 to the negative 6 inch an inch. But what I'm going to do is I'm going to make that micro inches just to help us out with our math, and we'll change it back later. So we'll have micro, inch, and inch. We'll do the same thing. Our strain 2 is going to be 400 times 10 to the 6 inch an inch, which equals 400 micro inches an inch. And then our strain 3 is going to equal 250 times 10 to the negative 6 inch an inch, which equals 250 micro inches an inch. And so one thing that's nice to know, here's our x and y. One thing that's nice to see is when we want to start our strain rosette equations is that our strain 2 is on the x-axis. So we can make our strain 2 equals strain x, which equals 400 micro inches an inch. And that's going to help us out because when we have our strain equations, we'll have 2 variables and 2 equations. So using a system of equations, we'll be able to find both of those and move on to more circle. So to start here, we'll start by showing the equation, which is going to be e to whatever symbol it is, equals the strain of the x cosine squared theta of that symbol, plus strain of y sine squared of theta of whatever that symbol would be, plus gamma xy cosine of theta symbol sine theta symbol. My gamma looks really bad. And so we're going to be using that equation. So starting with strain 1, we're going to plug in using our micro inches, negative 150 equals, we have even strain of x already, so that's going to be 400 cosine squared. Now for 1, you could either do negative 75 or you could do 285 and go around. I did negative 75 to save myself those microseconds of time, but you both wield the same answer. So negative 75 plus, we don't know the strain of y, so that's an unknown, sine squared, negative 75 plus our gamma xy cosine negative 75 sine negative 75. Oh, that barely fits. Okay. So doing the calculations, which I've already done, we'll have negative 176.795 equals 0.933 strain of y minus gamma xy over 4. So we're going to hold on to that for now. That's going to be our first system equation. Now we're going to use our strain rosette equations at strain 3. So now we're going to have 250, which I should put my units to follow. So I'm just going to save myself right now. Micro inches an inch equals our e of x, which we have 400 micro inches an inch times our cosine squared. Now we're using our 75, our positive 75 plus our strain in the y, we don't know yet, sine squared of our 75 plus our gamma xy cosine 75 sine 75. So then using that equation, when we isolate the variables, we're going to have 223.205 equals 0.933 strain of y plus gamma xy over 4. And so now here's our second. So putting these together, we can now do a system of equations to find our strains and our gamma xy. And so when we're doing this, we'll have negative 176.795 equals 0.93, I'm just writing them again, 933 epsilon y minus gamma xy over 4, and 223.205 equals 0.933 strain y plus gamma xy over 4. So this works well because we're able to cancel out our gamma right now and be left with one variable. And so when we add both of these two, we'll get 46.41 equals 1.866 strain of y, which comes out to have our strain of y to be 24.871 micro inches an inch. We're going to hold on to that, and right now I'm going to bring back down our strain of x just to keep everything together, 400 micro inches an inch. Now we need to find our gamma xy. And so how I do that is I just plug my strain back into our strain Rosette equations, and then that's how I can find my gamma xy. So I'm going to use this one right here, 223.205 equals 0.933, use my strain of y that I have now, micro inches an inch, and then plus our gamma xy over 4. So when we multiply this together and subtract down to the other side and then multiply 4, just to save time for the calcs, we're going to have gamma xy equals 800 microradians, and it's not in degrees. We're going to hold that there. So we're going to move this forward now. Okay, if it stays there, that'd be great. We're going to move this forward now, and we're going to start working on our Mohr circle so we can find our principal strains. And so where we're going to start right now is we can see our strain of x, y, and then we have our gamma. These are going to be pertinent to having our Mohr circle. And so we'll draw our axis. And so our x-axis is going to be strain, and our y we're going to have be gamma over 2. And so we're going to start. And so to start Mohr circle, we have to plot 2 points. And so we're going to first plot our strain of x, and the point's going to be our strain of x with a negative gamma xy. And so this is going to be a point that helps us find our diameter. And so we're going to mark right now a 400 micro inches an inch. That's going to be one of our points. I should have put on inside for the circle, but that's fine. And so right now, because we're doing gamma over 2, we're going to use the point 400. So this is going to be our 400 right here. Negative though, because we have to plot the negative gamma. Negative 400, and so we're going to have a point right about here. The next thing is to use our point where we plot the strain of y, which is going to be 24.871. It would be right about here, 24.871. And we're going to use that with our positive gamma xy, which is going to be over 2, so it's going to be 400 in the positive direction. When we find that, it will be right about here. The next thing I want to do is I want to find the center of what will eventually be our circle, but for now will be the center of our diameter. And so what I do is I add both of our left point and our right point together and divide it by 2 to find the average point, which will be our center. So our center is going to be 212.4355. Right here, 212.44. I'll just round it for the moment. And so now what we have is we have the diameter of our Mohr circle. And so what this does now is now we can visualize what should look like a circle, but for the sake of this video, it might look like an ellipse or a flat basketball, but that's fine. And so what I initially thought was I would have to go through this point, but it doesn't, because these points help us with the diameter, and these outer edges are eventually going to be our max and minimum strain that we find, and those will be our principal strains. And so for here, what we're first going to do is we're going to find out what this radius length is. And so how we can do that is by doing Pythagorean theorem. And so if we use the height we know right here, which I will draw out to be 400, and then we will find the length, which is from our left point to our center, which we could do by subtracting. We'll have our center and subtract what this length is, which comes out to be 187.57. We could find our radius. And so our radius will be 400 squared plus 187.57 squared, all to the square root, which our radius comes out to be 441.79. And so what's nice now is we can find our gamma max, because our gamma max is going to be the longest point within the circle, which is going to be the radius, or which is going to be what that length of radius is. So we're going to have our gamma max, which right now is over 2, equals the radius. And so when we isolate gamma max, we find that it's going to be that radius 441.79 times 2, which equals 883.58 microradians. We got to keep it in micro. And so we're going to hold that for now. Now we're going to go back to our principal strains. And so how we want to find our first strain is it's going to be the length of that center from the x-axis, and now we're going to add that radius, and that's how we're going to find our rightmost point, which will be our strain 1. So how we're going to do that is we're going to add that center length, which is 212.44, and then we're going to add from that the radius length, which is 441.79, which equals 654.23 micro inches an inch. There's our first one. And now we're gonna, strain 2 is gonna be the same thing. We're gonna add our center, but then subtract that radius so we could find our leftmost point. And so in doing so, we're gonna have 212.44 minus 441.79, which equals negative 229.36 micro inches an inch. So now we have our maximum strain, our minimum strain, and we also have our maximum gamma. And you would think we're done, but right now the question asks us to find our stress 1, our stress 2, and our tau max. And so we're not necessarily done yet. Now we've done more circles successfully, we found our principal strains, and we have to transform it using generalized Hooke's law. And so before we jump into that, we need to write some data down that we're gonna have to use. So our modulus of elasticity is going to be 10.1 times 10 to the 6 psi. That's going to be important. Our modulus of rigidity is going to be 3.7 times 10 to the 6 psi as well. And then our Poisson's ratio is going to be 0.33, which couldn't find in the book, but I found via peers and also the internet. So we're going to keep that for now. And that's going to be data we're going to use in Hooke's law. And so in using Hooke's law, it's helpful because we can use stress transformation to find all of our answers and what the stress is going to be. We can change that. And so when we want to find stress in the x direction, we're going to use the modulus of elasticity divided by 1 minus Poisson's ratio squared times our strain in the x, which for us is going to be our 1, plus Poisson's ratio times strain in the y, which is going to be our 2. And then for strain the y, it's going to be very simple, so I'm going to go a little faster. Modulus elasticity minus 1 minus Poisson's ratio squared, except these are going to flip-flop. So now we're going to have strain the y plus Poisson's ratio times strain the x, which, a reminder, this is 2 now, and this is equation 1. There we go. And then, so we're going to start there. We're going to input our numbers for our x, which is going to be our 1. So this is going to equal our modulus elasticity. Now, we want it in KSI, not PSI. So this is going to be times 10 to the 3rd, so we could have it in KSI. And so now we're going to have 10.1 times 10 to the 3rd divided by 1 minus 0.33 squared times our 1, our strain the x, which is going to be 654. But we have to change it from micro inches back to normal standard units so we can get that KSI. So 604.23 times 10 to the negative 6 plus Poisson's ratio times our strain the y, which is going to be our 2. I'm going to have to put it underneath for space, times 10 to the negative 6. There. And so through here, our strain the x is going to be found to be 6.56 KSI. And this is going to be a final answer, so we can box this. Now we're going to work on our strain the y. I'm going to move this direction, which will equal our 10.1 times 10 to the 3. And we're going to have that divided by 1 minus v squared, which is going to be Poisson's ratio again, times our strain 2, strain y, which is going to be negative 229.36 back to standard units, times 10 to the negative 6, plus Poisson's ratio. And then e of x, which is going to be our strain 1, which is going to be 654 0.23 times 10 to the negative 6. And if I was going to find a mistake, I should have my units in inch to inch, and that would be carried up here as well too. If I can go back, I would replace that. And so when we do this, we find out our stress in the y direction is going to be negative 0.153 KSI as well. So we're almost done now. We found both of our stresses that we want. Now we just need to find tau. So how we find tau is our gamma in the xy direction equals tau xy divided by the modulus of rigidity that we have up here, now changed to KSI. So when plugging into those numbers, we get 800 times 10 to the negative 6 inch, that's radians, sorry. Radians equals our tau xy divided by our 3.7 times 10 to the 3, and that's in KSI now. Multiply it together, you get tau xy equals 3.27 KSI. And from there, we should be finished. And so we started from having a strain rosette, and then through using strain rosette equations, we were able to find our strains to use for our Morse circle. And Morse circle, by using those, we were able to create our diameter, which was able to find our maximum and minimum strains available in our maximum gamma, which would be our principal strains. And from there, we used stress transformation through Hooke's law, and we were able to find our stress, both of our stresses, and we were able to find our tau xy. And to show that this is me, here is my signature, my sloppy signature. Awesome, thank you.